Hello again. This is the Pencrest High School AP Physics C video series. This is video 5E, rolling. So when we have something that is rolling, we have rotational motion and translational motion combined. We're going to restrict our analysis to what's called smooth rolling. In smooth rolling, there is no relative motion between the point of contact and the surface. So if we consider this object that we see on the screen rolling to the right, the point here where the object has contact with the surface is not sliding left or right relative to the surface. Now what we see is that there's a combination. If we look at the outer edge of this rotating object, we are familiar with the linear velocity that of the outer edge associated with the rotation. So that velocity equals omega times r, where omega is the angular velocity. If we consider the translational motion, the linear motion of the entire object as it moves to the right, the entire object is moving with the same linear velocity. So what we find is that, in particular, the point of contact, because there can't be any relative motion here, when we combine the two velocities, the one that's due to the rotation and the one that's due to the translation, they need to cancel out at the point of contact. So in other words, the linear velocity to the right here is equal to the linear velocity to the left due to the rotation. So they cancel out, and we find that this instantaneous velocity of the contact point is 0. We also see that at the top of the object, the point on the edge that's moving to the right, because those two velocities add up, we find that the top of the object is actually moving to the right at twice the velocity of the center of mass. So in order for these two to cancel out, we find that the magnitudes of the velocities due to translation and rotation at the edge of the object must be equal in order for them to cancel out here at the contact point. So what that means is that in order to be undergoing smooth rolling, the relationship between the linear velocity and the angular velocity is a familiar one. The velocity of the center of mass has to equal omega times r. Once again, in order for these two velocities to cancel out, this has to be the case. If the rolling object happens to be accelerating, and again, still smooth rolling with no contact, no motion between the object and the surface, it'll be accelerating in translation, or linear acceleration A, and it will have an angular acceleration alpha. The linear and rotational accelerations are related in the same way. So the linear acceleration of the object, A sub cm, equals alpha times r in cases of smooth rolling. We also find that the same relationship applies to the top of the object here. This point instantaneously would have a linear acceleration or a tangential acceleration equal to 2 times a sub cm. Now, an object that rolls across a horizontal surface at a constant velocity has no tendency to want to slide at the point of contact, so there's no friction force acting there. The normal gravitational and normal forces act, but since neither of those forces exerts any torque, because they act at the center of mass, the angular velocity is also constant. So we have a constant linear velocity v and a constant angular velocity omega, where, of course, v equals omega times r. If, however, the object is accelerating, then we have a friction force at the point of contact that is going to contribute the necessary torque that produces the angular acceleration alpha. So there's a few different situations that we can run across here. We have a wheel that has a horizontal force applied to its center of mass, so where the axle is. The wheel's inertia, its linear, its mass, and its rotational inertia resist changes to its motion. So what we're going to need here is a force equation for the wheel and a torque equation for the wheel. The applied force, because it's applied at the rotation axis, does not exert any torque. So the wheel, when this force is applied, the wheel wants to slide to the right. The friction is going to resist this motion and is going to point to the left. So again, we're going to need a force equation. We're familiar with that. The object is going to accelerate to the right. So Fa minus Ff equals ma. And then again, because the applied force is at the center of mass, it will not exert any torque, but the friction force will. This object is going to accelerate to the right, and it's going to rotate clockwise. It rotates clockwise with some alpha due to the torque that is applied by the friction force. So there's the friction force times the radius, which is how far away it is from the rotation axis, and then equals I times alpha. What allows this system of equations to be solved is when you put in the formula for I that you would get from the table, and then alpha, of course, is A over R, so that will allow you to combine the two equations, eliminate the friction force, solve for acceleration, etc. Now, if the applied force is off-center, or somewhere other than the rotation axis, then the applied force is going to exert what's called an external torque. And this is the key point that gives people trouble. The friction force is going to respond in such a way as to resist the external torque that's exerted by the applied force. So we have the same wheel here, but we're applying a force sort of lower on the object, or below the rotation axis. The important thing is that the applied force exerts, in this case, a counterclockwise torque that makes the object want to rotate counterclockwise. The friction force is going to respond to resist that torque. It's going to then exert a clockwise torque by applying the friction force to the left. Okay? So when we look at the at the force equation, it looks the same. Fa minus F equals ma. The torque equation looks a little different. Notice that the friction, the torque due to the friction force is clockwise and positive because that's the way the object is going to roll. This object is going to accelerate to the right. There's no way that it can roll counterclockwise and accelerate to the right and still undergo smooth rolling. Okay? So it's going to accelerate to the right. That means the applied force must be greater than the friction force, but it is going to roll in a clockwise direction, which means that the torque due to the friction force has to be greater than the torque due to the applied force. Once we get to this point, the analysis becomes the same. We put in the I term, we put in A over R for the alpha term, and then solve the system. Note in this equation that R2 applies to the distance that FA is applied from the central axis. So we have to be careful about where these forces are applied and what R's we use for each one. Now, if we have the same wheel, but the external force is applied at the top of the object or above the rotation axis, this is where it gets tricky. The applied force exerts a clockwise torque, and that means that the friction force will respond in such a way as to resist the clockwise torque. Notice that the friction force is to the right. That's definitely counterintuitive. We're not used to seeing that, but again, the external torque supersedes the external force, and the friction responds in such a way as to point to the right. Force equation is now Fa plus Ff equals ma. And then when we look at the torque equation, the applied force exerts the clockwise torque. That's got to be greater than the torque due to friction, so that, again, the object rolls in a clockwise direction because it's accelerating to the right. Okay? This is the tough one. So when you're looking at a situation like this with an applied force on a rolling object, be aware that the friction responds to resist the external torque that the applied force exerts. Okay? In all cases for smooth rolling, there is no relative motion between the object and the surface, so the friction force is static. It is not a kinetic friction force, even though the object is moving. There's no relative motion between the contact point and the surface, so the friction force is static. There is a maximum value of the friction force given by mu times Fn. The friction force is not necessarily equal to mu times Fn. Could be less because it's static friction. So there is an upper limit on the acceleration associated with smooth rolling. That upper limit on the acceleration is determined by the maximum friction force, the maximum static friction force that can be exerted between the object and the surface. Okay, so next up is ramps and rolling. Until then, enjoy, and I'll see you again soon.